Hello, Titans. I want to make a quick video here to describe the two gravitational potential energy equations that we know about. The first one is not a big deal. It says universal. It says potential energy, that's capital U, sub G equals mgh. Gravitational potential energy is mgh. No big deal with that. That says the higher we are, the more potential energy we have. If I lift, can't quite see my tabletop here, but if I have something sitting on the tabletop, my marker here, it has no potential energy because it's on the floor on the table. If I lift it, it has potential energy because we have a certain height. If I lift it twice as high, it has twice as much energy, 3 times, 4 times, 5 times. The farther above the table I get, the higher the energy. But remember, we also said that the zero position, I'm using the table as my zero position, is arbitrary. I could use a ceiling if I wanted to. I could say the ceiling is my zero position, in which case here I would be below the ceiling and I have a negative height. So I have negative potential energy. Here it's even more negative and even more negative and even more negative. That works. It's kind of a weird way of describing things, but it works. So what happens if we use this equation mgh as we lift things farther from the planet? I'm going to basically describe what I was just showing you there. If we're on the planet, we would say 0 joules of energy. If we lift it farther away, we might have 100 joules of energy, or 200 joules of energy, or 300 joules of energy, as we are increasing our mass higher and higher above the planet. Nothing fancy about that. But there is a problem with that. Because if we keep lifting something higher and higher and higher and higher above the planet, it feels like these values should get larger and larger and larger, and they would if we just do mgh. But imagine if we are far, far, far away, I mean, out of our solar system, far, far away from the Earth. Do you see a problem with that equation? I hope you recognize that little g, the acceleration of gravity at the surface of the Earth, is no longer 9.8 meters per second squared. We're far away from this planet. Little g is very small out there. In fact, if we're infinitely far away from our planet, that gravity approaches zero, and we'd get an answer of zero if we're far, far away. But that can't be right. We're going 100, 200, 300, 400, 500. We don't get zero when we keep adding energy. Something's got to give because this doesn't work. Well, what we're finding is that this equation, glorious as it is, close to the surface of the Earth, really kind of fails us when we start dealing with far larger distances. As we get farther and farther away from our planet, it starts to not work so well. Okay. Sort of like we saw when we were studying forces last fall. We found that near the surface of the Earth, we could say the forces are mg, and that worked great. But as we got farther and farther away from the planet, where g isn't 9.8 anymore, we had to use gravitational concepts like gmm over r squared, right? Okay. This is kind of the same deal. Turns out if we get far away from the planet, we've got to use a different version of this potential energy equation. Your equation sheet writes it with a capital G. You might recall capital G is the universal gravitational constant. That's what we used for things that are far larger distances. So we can write UG equals negative GMM over R squared, over R. That's GMM over R. Your equation sheet writes M1, M2. I like to write capital M, little m. No big deal, one way or the other. But that's our equation as we're trying to find our potential energy, our gravitational potential energy. You'll notice a couple things about that. First, it's a negative sign. Our energies are negative. That feels awkward. So here at the surface of the Earth, we have a negative gravitational potential energy. Well, okay, well, let's leave that on hold for a minute. What's the other issue? What if R gets huge? We're far away from the planet. As R approaches infinity, that is, as the numerator gets, the denominator gets bigger and bigger and bigger and bigger, you see UG getting smaller and smaller and smaller and smaller, essentially approaching zero. Meaning if we're infinitely far away from our planet, our gravitational potential energy is zero. which is sort of what we were talking about here a minute ago, but for different reasons. So, in fact, we're going to say that if we are far away from our planet at infinity, the energy is zero. It's kind of like we're treating infinity as the ceiling. And the values we're going to have as we get closer and closer to the Earth, as we get closer, our potential energy gets bigger and bigger and bigger, but it's, excuse me, yeah, bigger and bigger and bigger, but they're negative values, meaning right here, we might have a value of negative 100 joules. And down here, we might have negative 200 joules. And down here, we might have negative 300 joules and negative 400 joules and negative 500, negative 600, negative 700, negative 800. And maybe on the surface of the Earth, we have negative 900 joules. Those are negatives. Well, okay, this is weird. Negative energies don't make us feel comfortable. But again, if the ceiling is zero, the farther we are from the ceiling, the more negative we get. But I want you to notice something else. If we go from the surface of the Earth up into the air, a certain height, what happens to our energy? It goes from negative 900 to negative 800. Isn't negative 800 larger than negative 900? So haven't we gone up 100 joules? Much as we expected to with our other equation, we went up by 100 joules. If we go from 900 to 700, we've gone up by 200 joules, much as we would have done here. So this kind of makes it fit. Our convention is that we say zero is the ceiling at infinity, and we get increasingly negative values as we get closer to the surface of the Earth. So that equation, this equation, will really help us when we're dealing with large, large distances, and the numbers are always going to work. When we're close to the surface of the Earth for everyday problems, we can go ahead and just use MGH, and we are totally cool with that. Now, I want to do a sample problem. What if I want to throw a rock away from the Earth fast enough that it gets all the way out of the Earth's gravity well, if you will, all the way away from gravity from the Earth, till it's out there in the midst of the stars and gravity, the Earth's essentially not pulling on, at least not significantly. Of course, there's never a place, but if we're out in the middle of the other planets and stars, other things are pulling us just as much as we are. So let's treat it as I'm going to throw it all the way out and have it just come to rest far away from the Earth. What would happen to our mathematics here? Well, I'm going to think about the law of conservation of energy. E naught equals E. That works great. If I throw my pen up into the air, I can say I started with kinetic energy as it went up, and it turned into potential energy up here, and then it turns back into kinetic down here. And I can use the law of conservation of energy to find out how high it must have gone. I could also use kinematics, but that's okay. So this still works. Let's think about what's going on. At the beginning, I'm just throwing the rock up into the air. It's certainly got kinetic energy. It also has gravitational potential energy. It's going to be a negative value, but it's still gravitational potential energy. So I'm going to write UG. And how about at the end? It's all the way up away from the Earth, no kinetic energy. I'm going to argue that the K and the U, the K is zero, and at infinity, the energy gravitational is zero, and the whole right side of my equation drops out. Now, if I were to flesh this out a little bit, instead of K, I can write 1/2 mv squared. Instead of UG, I can write negative, so I'll change that to a minus, GMM over R equals 0. Okay. Now what? I'm going to add GMM over R to both sides. I can write 1/2 mv squared equals GMM over R. Now you might notice that the mass of the rock just dropped out of the problem, didn't it? Mass of the rock is the same on both sides. It drops away, leaving me with the mass of the Earth. It's doing the pulling. And in fact, if I double both sides to get rid of my fraction, because I don't like 1/2s, I can change that to say v squared equals 2 GM over R. And this is what we call the escape velocity of the Earth. That is, how fast would I have to throw a rock so that it escapes our Earth's gravity? Let's plug in some numbers. V is going to be the square root of 2 times G, that's 6.67 times 10 to the minus 11, meters cubed over kilograms seconds squared. You can look that up on your equation sheet if you don't remember it. I need the mass of the Earth. It's been a while since we dealt with that, but again, you can look it up. It's 5.98 times 10 to the 24th kilograms. We actually calculated that back in the day. Divided by the radius of the Earth. The Greek scientist Eratosthenes told us that was 6.38 times 10 to the 6th meters. I want you to notice we're not squaring that like we're used to from gravitational force problems. It's just meters. I want to check the units to make sure they're okay. I see meters cubed on the top and meters on the bottom. I'm going to cancel one of them. I'm going to make that meters squared. I see kilograms on the top and kilograms on the bottom. I'm going to cancel those. And I'm left with meters squared per second squared. If I square root that, I get a velocity in meters per second. Does that seem plausible? Absolutely. The number, I have it in my notes, but if you want to pause it and do the calculations, you certainly could. I have 11,182 meters per second. That is how fast I would have to throw a rock to get it to leave our Earth's gravitational field. Now, that's not a practical problem. I can't do that. In fact, NASA doesn't launch a rocket at 11,000 meters per second and have it just kind of coast all the way up to wherever they're going. No, what they do is they launch it slowly and get it higher and higher and higher. In fact, as the higher we go, as we go higher and higher, actually, let me look at this equation. This is our equation for the escape velocity of the Earth. As we get higher and higher and higher, that necessary velocity gets smaller and smaller and smaller, doesn't it? In fact, by the time we're quite a ways away from the Earth, that escape velocity is small enough that I don't need my rocket ship just screaming. I can have a smaller velocity. And that's kind of nice because we don't want to just launch something from the ground at tremendous velocities. We accelerate it more slowly. It goes faster and faster and faster. And somewhere up there, it reaches the point where it's going fast enough to escape our gravity. So that, I hope, works for you. By the way, I mentioned that's not a real practical thing we might do for the Earth. We don't launch things at that speed. But what if we were on the moon? In fact, when we first went to the moon, we were a little worried about that. And so they went back and did some calculations and found out what the escape velocity of the moon would be. You can calculate it if you want. You've got your equation. In fact, it's small enough that you can launch a golf ball off the planet. If you hit it hard enough, you can launch a velocity all the way out of the moon's gravitational field. There's a commercial, I think, that has that going on. But yeah, we can totally launch things all the way out of the moon's gravitational well. It's hard to do for the Earth, but it works for the moon, or perhaps for some other planets as well. All right. That is our basics. I think I might add another video later that's got a more complicated problem than this one, but at least this is a good start for us. And I hope this helps you understand kind of the setup of these two equations, when we would use our first one, mgh, when we're close to the surface of the Earth, when we would use our second one, gmm over r, when we're dealing with far larger distances. And then we can still use the law of conservation of energy just like we always have. Go physics. I hope you have a great day.